All right. Hello, my name is Alec and I did my project over optimized GPU-based thermal simulation for specifically CPU floor plans. A little bit about why I chose this topic. I remember at the beginning of the semester, Dr. Schubert was talking about how temperature is a major factor in chip design, and how we can only optimize the hardware so much, and after that, we really have to look at the layout of the chip. And so as the chips designed are getting faster and more dense, the heat from the transistor density builds up, and we have to do something about that. So if we can simulate the chip beforehand during the design process, it'll save a lot of money during fabrication. And this type of simulation is inherently really good for GPUs because it's naturally parallel. So just a little bit of the math background. I used the Poisson steady-state heat equation. As you can see right here, this zero is because of the steady state, and this is the temperature here, and you got Q, which is what will be generated later. It's the volumetric, it's the heat generation rate, and then just some other parameters here. And rearranging this and substituting for alpha, you can get this equation, which can be used for discretizing and implementing for our algorithm. So for discretizing, I used the Jacobi iteration method. This is the finite difference approximation with h here in the bottom. The denominator is the spacing between each element. And then here's a discretized form. It basically takes the four neighbors, the top, bottom, right, left, sums those, averages it, and then here is implemented into the previous equation. For the boundary conditions, I just use a very simple Dirichlet's boundary condition, which means all the boundary points are fixed. They're never going to change. For this, I used ambient temperature of 25 degrees Celsius, just for simplicity. That creates some unrealistic scenarios, but for the purpose of this demonstration, it's sufficient. It is not, this formula is not time dependent, it's time independent, so it just goes purely off iterations, and so I'll run it until convergence. That'll determine to be 0.001 change of the max element temperature between the previous temperature array and the current one. So here computing the current temperature element of the array uses the formula, and this is the previous, TK is the previous temperature from the previous computed array. So to get the power density map, Q, in the equation, it was proved difficult to find a realistic and accurate power density map because that's proprietary information. Manufacturers don't really want to release that. But I did find one through Hotspot, which is developed by the University of Virginia for thermal simulation of chips. In their examples, they had a floor plan for the Alpha EV6 processor. It's very old, but it was out there, and here's a little depiction of it. Each of these is a major component in the chip. So we got 16 millimeters square chip here, and you got your caches and ALUs in there and registers. That'll be used to compute the power density map. So for doing that, I inputted the floor plan file and the power trace file from Hotspot, and the power trace file is a realistic simulation of the power draw of each of those major block components, and for each iteration it's like a realistic program and at time steps. So I just took the very first row of the data for iteration 0 time equals 0 and broke it down a lot further into discretizing the entire 16 by 16 millimeter chip into 256 by 256 element blocks, and then I added some random noise in there to kind of get a more realistic interpretation, so have every major block constant. This was all normalized so that the sum of the the power was still the same. It was like 59 watts for the chip at that specific time interval. And then transforming to a power density map, it just divided by the area of the block element and how much power it used. So first, I implemented the algorithm serially. To do this, I used the Kodiak computer. So to start off, it initialized the Q array, T, this is the current, and then T new is the new computed temperature array from the algorithm. Then I went on to load power density map. I just had a separate Python script compute that from the previous slide, and then could load it in just in CSV format. Next, initialize the temperature array. Need to have a initialized value, so I just set everything to be ambient temperature, 25 degrees C. And then for the algorithm implementation, use the formula to compute each new element in T new, applied the boundary conditions, computed the max element-wise change, and then checked for that convergence of less than 0.001 difference, and then just copied the new array to current from the next iteration, and then just some data of the final values and execution time was recorded. All right, here's the serial implementation. To start off by setting some constants here. K is the thermal conductivity. I just assumed silicon for that material. The width, 16 millimeters, is from the floor plan file. And then function here loads the CSV file into Q. And then for the final outputted data, I have a few functions here. This is for the convergence, so determining the element-wise max change between the array. And then here, just like I said before, the outputted min-max average of the final T new array after convergence. Getting here into main, we have initializing all the three arrays, the 256 by 256, so about 65,000 elements total, loading the power map in from the CSV file, initializing the current T array to start with 25 degrees C, that I discussed in the slide. And then here getting into the actual algorithm, I set a max iterations just for testing. That's just to make sure it doesn't blow up and runs forever. But it'll converge before that. I set that to about 50,000, and then it'll finish before then. But here's the updating the temperature. That's the equation implemented right here. So we have updated our T new array using the current T array, and then here's the power density map element, and then just averaging those. Applying the boundary conditions, that's just setting all the borders to ambient temperature, 25 degrees, compute the match change, and then using that function from above, and then check for convergence, and then end the loop if it's achieved. And this is just printing some data as we go along. And then here's just swapping we're copying the new array to the T array for the next iteration. And then final results are right here. Just printing the min-max average. I saved this so that I could graph it later and show the output. This right here is a heat map of the final output T new array. So you can see that the boundary conditions are really unrealistic because they're really clamped down to 25 C. So that's going to impact the temperature distribution at the end. But right here around, this is about where we had the highest power draw, and that's where we ended up with the highest temperature. Ended up being about 130 degrees C is the highest temperature. this is unrealistic because it's not like calculating, accounting for heat sink or lateral heat dispersion through the heat sink. But the purpose of this project is mostly for implementing a parallel version and optimizing that. All right, here's some more results. As I said, 130C was the final temp, but this is what's interesting here. The total execution time over 30 seconds, so quite a bit. We'll see that improved once we get into the CUDA version, but just some interesting data here. The max temp gradually increases, and so it levels out at convergence, and the convergence right here really spikes at the beginning when there's a lot of change, and then levels out as everything equalizes. All right, for the CUDA naive implementation, I implemented the same general algorithm, but instead of having serial, went parallel with CUDA, and this included a main file and then a kernel.cu. So in the main, assigned constant parameters, just kind of the setup stuff as before. This is the same as before, load power density map. And then for each array, QT and T new, initialized and allocated a host version and a device version. Copied the data from the host to device after setting the current T to ambient temperature to start the algorithm. Define the grid and block dimensions. I used 16 by 16, 256. It's easily divisible by 32, and it's naturally good since we have 256 by 256 elements. It just keeps everything clean. I tried some other dimensions, but this is the best performance I got. All right, and then going into the kernel, CUDA kernel launch, each thread is now going to compute an element in the T new array. So instead of having an unnecessary loop there, each thread will be launched and compute its own new element. So about 65,000 threads will be launched. I'll copy the entire T new array every iteration back into host memory and use that same function as before to compute the match change element-wise, check for convergence, swap T2 and T new pointers. No need to copy anymore, can just swap the pointers. And then print the same information as before, and I rewrote the verification check function from Schubert's labs to just check that we have the same results as the serial version, and then free memory and print execution times that were tracked. All right, here's the main.cu file for the naive version. Setting up the constants as before here. That's pretty much the same. So load the power map. This is the same. And then here, start getting into the CUDA specific part, initializing our host variables. These are the QH, TH, T new H arrays. Allocate the host memory here. Load the power map. Allocate device variables. Allocate some device memory for those variables here. Copy the host memory or host variables to device. And then finally, here we get into the meat of the algorithm here. Launching the kernel. Here's the grid and block dimensions here. And then iterations the same as before, 50,000. And then here's launching the kernel. Input that, and each thread will perform its own element calculation. I'm tracking the time here for later on. And then this is copying the host memory. I have to copy both arrays back. So the TH, the T and the T new. To copy that back because this mass absolute difference function will need both arrays to compute the max change in each element. And then convergence check as before, swap the pointers, copy the final device T new into host memory, print the final results, and then free all the variables, arrays are allocated, and then print some final information there. All right, so running it, let's see, run with MPP run. Should be pretty quick, a lot faster than 30 seconds. Let's see, 67, there we go. All right, so right here, 3.75 seconds, so much improvement over the 30 seconds for the serial version. But we can see here that the kernel itself only took 0.07 seconds. That's for the computing the temperature. But the time for finding the max difference in the convergence check was mostly the majority of the time. This is copying back, so copying all 65,000 elements back into host memory every iteration is costly in time, as well as finding the max difference just through a serial for loop. So looking at speeding this up, we can implement a device side check for this, because this in itself is also parallelizable. So we'll look at that next. All right, as I said before, from the results, if you calculate it, 93% of the total execution time is spent just copying both arrays back into host memory and computing the max change for the convergence check. To speed this up, you can use a second CUDA kernel to parallelize the calculation of the max temp change values. And for that, I used reduction. So here's a depiction of the reduction algorithm here. We'll start with a stride. I'm using 256 blocks. So I'll start at 128. Pretend this is 128 here. And then each time it'll divide. It'll be like log 2 of n, or ln 2 of n, time complexity. And so every time this is halving the number of active threads, and eventually it gets down to just one element left, with actually comparing each max value. And then this element can be written back into host memory for each block, which means that there will only be 256 elements written back into host memory instead of 65,000. So a serial version of finding the max in 256 elements is a lot better than 65,000. I don't think for the naive version, I explained the kernel file. The compute temperature function here, kernel function, is the same for this implementation. I just added the max diff reduction. So going through this real quick. This is the boundary check, returns if we're out of bounds. The derelict conditions here assign all the boundaries with 25 degrees C, and then just implementing code that equation from the beginning of the presentation. This is each of the top, bottom, left, right neighbors. This is just calculating from these indices here. Coefficient simple here, and then this is updating the new T array right here. Okay, now getting into the reduction kernel. The indices are similar. This is launching I just hard-coded this since I knew I'd be using 256, and it was easier to go with the math here if I could visualize it. This wasn't changed throughout the course of the project. This will launch 250, for each block. There'll be 256 blocks that will each reduce the max change from each. So 256 times 256 is 65,000 for our total number of elements. So this we'll calculate the difference for each thread here, and then implement the reduction algorithm. So I said we're starting with a stride of 128 from the diagram. We'll just keep going until this gets to 0, and each time it halves. So reducing each time by half the number of elements that have to be compared. This is just right here, put it into this shared memory that was initialized at the top. It'll be size 256. Just comparing the current element was adding the stride, and once that gets down to 0, it'll exit this loop, and then the max difference that'll be passed in, it'll be array passed in, will just be assigned the value right at data 0. And so the max difference array will then be size 256, and that can be copied into host memory, and a serial check or serial max can be computed and then checked for convergence. All right, now I'm going to run the new and improved device side reduction for the max temperature. See if this is even faster. Yes, it is. All right, so before it was about 3.6 seconds. Now we're down to just over half a second. And if you remember, the total copy time before was about 2 seconds. Now we're down to 0.13 because it's 256 elements per iteration instead of 65,000 back to host. It also means that reducing it on the serial reduction down to 1 value is a lot faster as well, just over 0.01 seconds there. So I think that's about a 5x speed up from the naive version. All right, it was actually a 5.97 x speed up over the naive version. However, calculating my arithmetic intensity is quite low, 0.16, showing definitely in the memory bound region. That's mostly due to, this is for the compute temperature kernel, I'm having to use doubles instead of floats specifically for the power density because it's such high values. I need high precision since we're summing these small differences up over many iterations. It has to be really fine detail. So I tried to use floats instead, which would have instead of 8 bytes, it'd be 4 bytes per memory transfer. However, like I said, it needed to sum up a lot of those smaller differences, and I wasn't getting the same results. So instead, I tried to implement shared memory and multiple elements per thread. However, that did not increase the execution time, possibly due to just still being memory bound and that not really having an impact on the execution time and having to do a lot more boundary checks, which added just additional logic into the program. However, both of those kernel functions, since they're using most of the same data, they can be combined into one kernel, so can cut down on the launch time for actually setting up the kernel and initializing it. Instead of 2, you can just do 1. Additionally, instead of computing to the coefficient in the temperature array every time, can lower the number of arithmetic calculations in the arithmetic intensity calculation by 2 by just passing in the same value every time since it's using the same value there. Alright, this is the final kernel.cu implementation. I kept it as compute temperature. This is the just calculating the indices here that'll be used. Shared memory, data, that's the same as before. That'll be for the reduction algorithm. And then here, in this check here, this is combining the temperature computation, boundary conditions, and the difference calculation for the convergence check. Here is just for the derelict boundaries, setting the borders to 25 degrees C, and then getting all the neighbors surrounding the element here, and using that for the temperature check or the temperature calculation. And then finally, inside the same conditional, we have calculated the difference. This will be used for the reduction algorithm down here. This is the same before, but just instead of hard coding 128, kind of generalize this. So this is 16, this is 16, so 256 divided by 2 is 128, and the rest of this is just the same as before. And then finally, that max diff is copied back into the global over here, or the zero element value at the shared array is copied back into the max difference array that's passed in the top. And this has remained the same since the serial version. All right, and running the final implementation. The last implementation was 0.59 seconds. This final version is 0.51. So not as big as the speed up as last time, but definitely still a speed up. The copy time is roughly the same. The difference comes in here of this is a combined kernel, so it is more than the two-mature kernel before, but combining that just reduces some of that launch at this time at the start of the second kernel, simplifying things as well in code. All right, going back to this slide here, the results of the final implementation can be seen here. So I calculated all this. The first run was 0.661 for the time before, but you can see that allocated device variables is a big chunk. That's going to be hard to get around unless we can use floats instead of doubles. This copy time is still a major proportion of the data, but it's instead of being about 90%, it's a lot less than that. So we improved that there, and then this kernel time here for the temperature was a lot lower than, relatively speaking, from the others. All right, and looking at the final results of each implementation, the serial version was over 30 seconds, almost 31, and we had about a 6 times speed up down to the naive version, just parallelizing everything, just over 3.5 seconds. And then here's the reduction and the merged kernel. End up being this is relative to the naive version, so final speed up of 584% faster, and this would be like 6,000% over the serial version. So I hope you enjoyed my presentation and the advantages of GPU parallelizing a program over serial for this application. Thanks.